Hi, I'm Professor Seth Chandler from the University of Houston Law Center. Today's video is on ensemble methods in supervised machine learning. It's part of a series of lectures in the course Analytic Methods for Lawyers. What we're going to be looking at are three types of ensemble methods: bagging, boosting, and stacking. And what they have in common is that they rest on the notion that it's often better in having a good predictor or classifier to have multiple models instead of a single model and figure out some way of combining the results. And actually, there's a great analogy in the law that's basically a jury instead of a judge. What I want to do here is to show you how these work at a conceptual level. I'm not going to develop any state-of-the-art implementations of these methods. The other thing to keep in mind is that boosting is pretty challenging and stacking isn't so easy either, but I'm going to try and make sense of all of it. All right, let's start with bagging. It's the easiest one of them. And the main purpose of bagging is to avoid overfitting by withholding some of the data from the classifier and in effect forcing it to generalize. By withholding some noisy data points, you basically stop the machine from chasing noise. So what we're going to do is withhold data randomly, build multiple classifiers, each using its own set of data, and then figure out some way to combine it. And again, if you think of this like a jury, where each juror sort of remembers some subset of the facts, but maybe not all of them, I think you can see one of the ideas behind bagging. All right, let's start with the wine training data. The wine data, I think we've seen this before. It's on the quality of wines, or the alleged quality of wines. And what we're going to do is we're going to convert it from a regression or a prediction problem into a classification problem. So we'll import the raw data, training and test, and then if your wine gets above a 7, or a 7 or above, you're classified as good. If your wine is less than or equal to 5, then it's bad, and otherwise, which is basically the wine is equal to true, it's considered fair. So I'm going to apply that function, this which function, which is sort of a generalized if function, to the training data, applying that function to everything in the second part. Remember how this data looks. It's a list of rules. The second part is the dependent variable, the target, what you're trying to predict. And so we'll do that for the training data and for the test data. Almost forgot, let's evaluate all this. Great. All right, let's create our bagging function, and the idea here is that we are going to take our data and then we are going to use random sample. Random sample samples without replacement. So once you take a data point, you can't duplicate it again. How many of them should we take? Well, let's multiply n, which has this default value here, figured out by clever mathematicians as generally optimal, by the number of data points that we have. That could be a fraction, so we'll round it. So now we've got a random sample of the data, and now we're going to use random choice, which samples with replacement, to restore the original length of the data. That is, we're going to say, however, if you had 58 data points, I want your new data set to have 58 data points. So that's what bagging does, not a very hard function. Let's seed our random number generator. And now for an unfortunate problem. What I really like is to just use some shallow decision trees and to use bagging with that. Unfortunately, Wolfram doesn't currently support shallow decision trees. They figured, well, why should we make them extra shallow? Let's come up with deep decision trees that work well. But for bagging, you may want shallow decision trees. But there is a way of hacking and creating them, and that's to use random forest, the random forest method. Random forests, we'll talk about them in a future video, but they're basically a whole bunch of trees that vote. And we can, random forest has more options than does decision tree presently. So all you have to do is say, I want a random forest that has one tree. And a random forest with one tree is a decision tree. The only other thing I need to do is say, hey, use all the features every time, at least consider all the features every time, because random forests don't do that, but my decision tree does. And then I want the ability to control the maximum number of cases that you have to have before you won't split anymore. So I might say, look, if there are 50 homes or 50 bottles of wine or 50 whatever in a leaf, that's enough. Don't split it any further. Okay? So we can control that by setting the leaf size option. There's some code here that I don't feel you need to understand. It uses things like options pattern, option value, and some other advanced features. Just know that by the end of the day, when you have shallow decision tree, it's basically just a kind of classification. So what we're now going to do is we're going to create a jury of 12 decision trees. And really, you're not supposed to see this because it wasn't supposed to have been evaluated yet. I cheated to make sure this all worked. Ooh dear. Okay. Great. So let's run our shallow decision tree on bagged wine training. That is, so the data size will be, the data samples will be different each time. I'm going to say once you've gotten down to 200 bottles of wine, I want you to stop. I don't want to see all the reporting about how you're doing and performing the classification, because that actually takes more time than the classification. A jury has 12 people. And augmented terse is this, basically it's the same thing as this through terse dimensions business. It's a resource function that I've written that hasn't been approved yet, which is why it's gray and not approved orange, but still it's publicly available and you can use it. Okay, let's create 12 shallow decision trees. And we'll count this, it'll take a few seconds to do it, and we're done. All right, and there are our 12 decision trees. Now, what we're going to do is see how they perform. The way I'm going to do that is I'm going to take all our jury, and for each juror, the juror is a function, and apply it to the features and get the probabilities. Then we'll have probabilities for each bottle of wine, but what I want to do is to show how each juror votes, so we'll do a transpose of that. All right, we can see that Juror 1, as with respect to the first bottle of wine, thought it was fair. Actually, it looks like Juror 2 agreed. But what we're now going to do is we're going to compute the mean vote amongst the jurors about what the probabilities were regarding each bottle of wine. Okay, so we now have it, and we can see that the first bottle, the majority thought it was fair, and the second bottle, a plurality thought it was bad, and the last bottle, a plurality thought it was good. So we can now see how the classifier performs. Instead of inputting a classifier function here, you can actually just input the probabilities in the form of a list of associations, and then this is the real value of how the wine is, or the supposed real value. And so what we see is we get 50% accuracy, which is actually, we'll see how decent that is, but I'm going to say it's not so bad. We can look at 4 classifier measurement objects to see how we're performing, and we can see that, I'm sorry, the accuracy is 49%, not 50%. We can see what our accuracy looks like, our Cohen-Kappa statistic, the area under the curve. We can see we're much more successful figuring out what bad wine is, and good wine is next. Figuring out what's fair wine, which is that only value of 6, is a little more difficult, and that's our mean cross entropy. We can compare how we do on a bagged classifier with using just a decision tree, not a shallow decision tree, but a nice hearty decision tree, a deep one, on our wine training data. And then let's see how it performs on the test data. So it's doing its thing, still doing its thing. Almost there. And we are just about around done, I think. Good, we're done. And so let's look at our statistics. Accuracy is actually a little lower than for our bag method. Cohen kappa lower, cross entropy higher. And so bagging here actually worked. It wasn't fantastic, but what we found was by withholding some of the data from the data set, we did better in every measure. And so what I did was to basically stop the decision tree from chasing noise by withholding data. And it turns out that bagging and a little more is going to be the key to the random forest when we see that. Now it's time to discuss boosting. And I played around with 2 opening sentences for this section of the essay. Here's my first version. Of the ensemble methods addressed here, boosting is definitely the most difficult to understand. Then I got more optimistic and tried sentence 2. Although boosting may seem complicated, and can get complicated if you get bogged down in the details, it's actually easy if you see it as a series of approximations. So I'm going to let you figure out at some point, watching this video and reading the essay, which of those sentences you think I should have started this section with. Let me see if I can just try to explain it in plain English. You have some learning algorithm called the base learner. And if it's not very accurate, that's fine. What you want is something that's really fast to train, it executes fast once it's trained, and you need to make darn sure it doesn't overfit. For people who like bias and variance, it can have high bias, but it should have low variance. In essence, think of it as a quick reaction to your data. You see the data, and you make a judgment what the rule is. Now, you're going to make mistakes when you do it quickly. But here's what you do. You now look at your features, and you look at the size of the mistakes you made, and you come up with a theory, a quick theory, of how you can best correct those mistakes. And your new theory is the additive sum of your old theory, your quick first reaction, plus you move in the direction, not all the way, because that would be chasing noise, but you move in the direction of correcting your mistakes based on that quick reaction. When you do that, you're still making mistakes. You're still not getting very good predictions, but you're probably closer. And now you look at your features again, and you look at your new mistakes, and you come up with a quick theory of how I can fix that. And you add that in, but not all the way, just a little piece of the correction. And you keep doing that and doing that over and over again. You keep seeing what mistakes you're ending up making, and you move in the direction of correcting your mistakes, but not all the way. And it turns out that by repeatedly moving towards correction of your mistakes, even with quick, inaccurate reactions, you tend to converge on the truth. You want to find patterns in your mistakes and try to compensate for them, but to do so slowly. All right, let's be a little more rigorous. What I'm going to describe is a variant of gradient boosting. There are lots of different flavors of boosting. I think this is actually the easiest one to understand. So we're going to start off with an incredibly simple model. I'll call it F0. And F0 has the property that no matter what data it sees, it always yields the same thing. And since it's yielding the same thing all the time, it might as well be the maximum likelihood estimator or the average. It just says every house is average. Now that is a terrible machine learning algorithm because it doesn't take any advantage of the data. But as I mentioned, if you're going to pick some constant, you might as well pick the mean. All right, so here's our model. y equals f0 of x. And I'm going to give f0 another name. I'm going to call it capital F0. All right, from here on in, we're going to do something a little bit different. We have our initial model that just picks the mean, but now we're going to start using the data. But we want to use a weak machine learning method, one that doesn't predict or classify all that well because it has high bias. So maybe a decision tree that could split the data only once, or imagine a regression tree that could split the data, not spit the data, only once. And you want an algorithm that's going to run fast, because we're going to be running it many times. You want it to execute fast, and you want it to do a little better than just guessing the mean all the time. So this algorithm that we're going to use to make our boosting model is called a base learner. Here's the other piece that's important. Instead of running the base learner on the features and the underlying dependent variable, like the price of a home in Boston or the quality of the wine, we're going to run it on the features and the associated cumulative residuals left over from the prior model. That is, what you're going to do is you're going to run the base learner. Yes, you're going to use the features. Is the home near a freeway? What's the nitrous oxide concentration? All that stuff that we've seen. But you don't want it to predict the house value. You want it to predict your mistake in the house value. So here what we're going to do is we're going to say, look, our residuals are equal to the difference between the true value y and our initial guess. And then what we want to do is we want to come up with a new function, little f1, that predicts this residual. Now, we'll do it. We'll come up with some function, some model, some regression tree, something. And what we don't want to do at that point is to just add our results to our original prediction. That would be chasing noise. That would be basically saying, well, we made a mistake and now let's fix 100% of the mistake. No. That leads to massive overfitting. But we do want to move in the direction of our mistake. So if we were supposing we were 4 off and our new predictor says you should move 3 up, maybe you move 3/10 in the right direction. How far you move is determined by this value nu. That's a Greek nu, not an English v. That's a learning rate. It's something we'll see in the future in other machine learning algorithms. It should be small, maybe like 0.1. And so now our new model, f1 of x, is equal to our old model plus nu, our learning rate, times the function that we learned on the residuals. Here's another way we could write that. And now we've started boosting. We had our original model and we're boosting it up. Let's do it again. Let's compute the residuals based on f1. Call those r1. And now use some weak learning method, probably the same method, to predict the new residuals. And so what's our new model? Our new model is our old model plus nu, our learning rate, times our new prediction of the residuals. And we keep doing it over and over again. The idea is to analyze your mistakes and move a little bit in the direction you need to avoid them. Here's the magical formula. Capital F t of x, our new model, is equal to our old model plus nu times our prediction of the residuals. And it turns out that if you do this a lot of times, it works pretty well, even if you start with weak base predictors. A note. What I've just described is called gradient boosting. There's another method that's sort of the same flavor. It's called Adaboost. In Adaboost, you don't change what you're trying to predict. That is, you don't have this business of trying to predict residuals. You're predicting the original targets. But what you do is you change the weights each data point is given in that machine learning algorithm. And in particular, you weight the data on which you've made mistakes. So at least you fix the mistakes. And then you rerun the algorithm, and then you see, well, now we have new mistakes. Maybe we got something wrong that we got right before. And so you keep running the algorithm based on changing weights. That's the Adaboost. It's a little more difficult to program, and I think it's easier to just see gradient boosting, so that's what I'm going to use. Okay, let's try gradient boosting on the Boston housing data that we're very familiar with. And I'm going to use a regression tree. And I'm going to use that same hack that I used with classifiers to come up with a variant of a shallow regression tree. I'm going to, because I don't want a big fancy regression tree. I want a shallow regression tree that predicts okay, not great, and it works fast. So what I'm going to do is random forest basically gives me the amount of control that I need, and a decision tree is just one tree in a forest. So again, I'm going to say let there be one tree, use all the data. A real random forest, for reasons we'll discuss later, actually uses not all of the features at once. It randomly picks features to look at. For our decision tree, we'll look at all the features, and I'll set our leaf size. You don't need to understand this code, but let's actually show you how this all works. Let's suck in the Boston. First of all, it is actually evaluated because I've been playing around with the stuff. Let's suck in the Boston data. All right, here's what the data means. And now here's our code. Shallow regression tree predictor. Our first argument is a rule of the features, remember that's in part 1 of the data, to our targets. Then we have options. Let's let the leaf size be 30. In other words, once you get down, you only have 30 homes in the leaf, don't split it anymore. And training progress reporting, I think we've talked about, it spits out information on what it's seeing as it goes through the training process. As it turns out, it actually takes more time to produce that than it does to just do the darn regression, and I don't think it's essential, so we're going to set it to none. And then what I want to compute is how well we're doing on data that it's never seen before. So we're going to create a Predictor Measurements object at the end out of our predictor function. So let's run this, and we're done. That was nice. And you can see it's not such a great predictor. It's got a 0.455 r squared. And the other thing you can see is that our predictor can only create 4 values because probably there are only 4 leaves in our one tree in our random forest. So the housing prices are spread out all over the place. That's why you're seeing these vertical lines here. But our regression tree is limited in its ability to work. And you might think that that means it's going to be cruddy and we're never going to get anywhere. But it's actually going to turn out, as you'll see, to work decently. We can compare this, by the way, with a conventional deep decision tree. Here I'm not going to use my random forest hack. I'll just use the out-of-the-box decision tree, which can go fairly deeply. Same data format here, same don't tell me about what you're doing, and we'll test it on we'll see how it does on the test data. And the first thing you can see is, first of all, we have a much higher r squared, and then the second thing you can see is 1, 2, 3, 4, 5, 6. So an unconstrained decision tree had 6 leaves and it's able to predict better. But let's see if with boosting we can turn our wimpy little few leaf decision tree into a mighty predictor. Okay, something about the mighty oak might be here. All right, so we need some code here, and we're going to do this code in 2 steps. First, we're going to do what is one step of boosting. That's what the boost step code does here. And ultimately, after I explain to you what nest does, we're going to use boost, which is mostly just using boost step in conjunction with nest list. So let's just walk through this boost step function, because this might learn some coding here. All right, so we're going to start off with this first argument being a state. A state is an association. What keys does it need to contain? It needs to contain all of the following keys: a prediction, a predictor function, and residuals. All right, what's our second argument? Our second argument is our features. That's a matrix. That's like all those left-hand sides of those housing rules. That's what we want. The target is a vector. That's all the prices. A base learner is something like a shallow regression tree predictor. could just be classify, predict, but we're probably going to use something snazzier. And here we're going to set a default value for new, our learning rate, which should be 0.1. I don't know what that's doing there. All right, so let's walk through this. We're going to have some local variables, a boosted target, data, pre, mo, delta, and new prediction. So what's the boosted target? What are we heading for? What we want to predict is the target, that's the actual value, less our current prediction. That's our residual, right? That's what we're trying to predict. So here's the form the data is going to take. The features are on the left-hand side, and that boosted target is what we're trying is on the right-hand side. We're going to apply our base learner to the data, and then we're going to compute a predictor measurements object, applying that base learner to the data. Then we're going to calculate how far we need to move by taking our features, applying our base learner to it, and then multiplying that by new, our learning rate. That'll give us the amount that we need to move, and then we'll come up with a new prediction. Our new prediction is our old prediction plus the amount that we should move. And then we're just going to spit out a new association. A new association, the prediction is the new prediction. The predictor function, I could have either put pre here, or I'm going to make sure it comes out of the predictor measurements object. So it's the predictor function property of the predictor measurements object. And what are our residuals? Our residuals are the residuals calculated from the predictor measurements object. Again, I could have done it probably in a different way, but that's the cleanest way. All right, that's our step. So we start with an association and some stuff, and out pops an association. Now for a digression on nest list. Nest list is a wonderful function that implements iteration. And here, the best way to see what it does is just look at an example. 3 arguments, function, initial value, how many times do you want to iterate? So it starts off with the initial value. We apply f, we get f of x. Then we apply f to that, and we get f of x. And then we apply f to that, and we get f of f of f of x. And then we apply f to that, and we get f of f of f of f of x. So that's what it does. Let's take a concrete example. Here's a function that says if the number is even, then divide it by 2. And if it's odd, multiply it by 3 and add 1. By the way, this is what happens to this is probably the most famous unsolved math problem that exists right now. So we're not going to solve it here, but you can at least see what happens. Our initial value will be 67, and we'll run it for 20 steps. And it seems to go up, and then it goes down, and then it goes up, blah, blah, blah. All right, so that's what nest list does. The unsolved question is, does it always basically stop and get down to a cycle of 421, 421, etc.? And the answer is nobody knows. So if you just want the last element of the list, like the 20, then you can run it. You can just say nest rather than nest list. The fact that it ends in 20 and I ran it for 20 times is a complete coincidence. Maybe I should do this. All right. So boost, the function boost that I'm going to build relies on nest list and boost step. Here's the idea. Start off with some initial value. That's going to be a state, right? Same code. How many times are we going to run it? We're going to run it iters time. That's right here in our function arguments. Again, let's do that. And then we're just going to boost step and take iters time. We're going to start with a state. It's going to take the features on the target, the base learner, and the learning rate, and it's going to run this, and out it's going to pop a new state. And then we're going to get a new state, and a new state, and a new state, and a new state. And that's how it works. So to do this, we just need to come up with an initial state. The prediction is every house's average. Okay, it's the mean of the house prices, and how many values do we need? Well, for every value in Boston training, we need a value of a prediction. What's our predictor function? Our predictor function to start out with is take the mean of the target. What are residuals? We're just going to subtract what we just calculated, the mean value of homes less the actual value of homes. And I don't know if I've talked about augmented terse before, but it's just a way of showing you a representative sample of the data and its dimensions. So here is our state as we start off. Here are all our predictions, and every single prediction is 22.7145, all 338 of them. Our predictor function is this mean function, and there are all our residuals. Those are our mistakes that we start with. Okay. Now, let's create a weak predictor. We'll use a shallow regression tree predictor. We'll set the leaf size to 30, no reporting. And I guess that's been evaluated, but let's just make sure it's evaluated. And let's run it. Let's run one step from state 0. And you'll see that some of the points are beginning to move. Now this is 23.6429. This is 21.7861. If I had set this learning rate to say 0.7, you would see the movement is bigger, right? Because we're moving more towards the direction of correcting our mistakes. But let's get it back to 0.1, which is a much healthier learning rate. All right, so now we're ready to actually do it. We are ready. And here's our function, boosted. That's what we're going to do. It's going to be a list of states. We're going to iterate, boost step. Here's our features. Here's our target. So here's our target. Here's our predictor. Here's our learning rate. So this is the function that we're going to iterate. Here's our initial state that we just created. And we're going to do it 50 times. And before I do that, I'm going to save because you never can tell what's going to happen. And when we're done, I'm going to print out about 12 lines of stuff if I possibly can. So here we go. It should take less than a minute. Maybe you could play the Jeopardy music at this point. But it's calculating a lot of trees, a lot of regression trees. If this were a real class, I'd say, does anyone have questions? But on this video, I can't do that. So maybe we'll come back when it's done. Yeah, if I'd hung in there for about another 20 seconds, we would have been done. But here we go. So what we want to see is how are the residuals converging as the boosting process proceeds? Are they staying the same? Are they going all over the place? Let's do that. And the way we're going to do that is here's our initial target. And we're going to take boosted. We're going to figure out the residuals of each iteration. We're going to transpose those. So instead of having the residuals per iteration, what I want to show is the residual of each point as we march through. And then this is just some plotting code. So what we see is that the residuals of most of the points start to shrink as we boost. There's usually one or two that are nasty. See this guy here? He doesn't seem to really be converging, and this one is a slow converger. But in general, we're making good progress. And you all can see, by the way, that we're kind of stabilizing here. It doesn't look like we're making much progress on most of these after, say, the 40th iteration or so. But on some of them seem to converge pretty fast, others more slowly. We can also see how the R-squared of the model increases as we keep boosting. Here's some code that does that. I think I'll let you figure out how that works. We're going to sort of hand code an R-squared here as the reduction in some of the squared residuals from our original model to our the current model. And so what you can see is that our R-squared on the test data increases nicely as we keep boosting away, and it kind of looks like it's asymptotically approaching, I don't know, 0.85 or something. But of course, this is on the test data. What we want to do is see how does it work on data it's never seen before. To do that, we're going to have to actually make a composite function out of all the little learners we found on the way, the code here is a little bit sophisticated, but the idea is we're going to take all our models and apply them to the points, and we're going to use through to apply all those functions at once. We'll add them up, we'll multiply it by the learning rate, we'll add in our initial model, that's that mean thing, and we'll get a function that is our cumulative model. So this is going to take well, when we actually do it, it's going to take a few moments. And then we're going to take our model based on our list of boosted states and map it over our all the test data. All right. So let's do that. And again, I'll take a break here because this is going to take a moment just because of the way I've constructed this. It's about 30 seconds later. We're done. Now we can see how well we did. Here are our boosted predictions. Here are the actual targets. We'll run predictor measurements on it. And that's looking nice. Look at that R squared, 0.77. The points are kind of lining up. Yes, there are some here that are pesky, but this is something that I'm feeling pretty good about. Okay, so let's see how that compares. Boosting a very weak predictor compares with a fancy predictor. Here I'll use a neural network. Okay, and we're going to use predict on the Boston training data. And this is actually going to take a little bit of time as well. And I think I will fast forward to when it's done. We're done, and actually it wasn't any faster than my boosting. The out-of-the-box neural network thing in Wolfram language is not the fastest implementation. Let's see how we do. Let's compute our R squared. 0.81. So today it was a little better. I've had better results in the past, but at least we're in the same ballpark. And so perhaps what we can say is that boosting a weak predictor does seem to work reasonably well. It's certainly better than using a raw weak predictor. The other thing, as it turns out, is that if I had tweaked the permissible, where do I set it? All the way up here, maybe. If I set the leaf size differently, we sometimes get a little better or sometimes a little worse results. It seems to be kind of sensitive to that. All right, so it's now up to you to figure out which was right. Sentence 1. Of the ensemble methods addressed here, boosting is definitely the most difficult to understand. Sentence 2. Although boosting may seem complicated and can get complicated if one gets bogged down in the details, it's actually easy if you see it as a series of approximations. Extra credit. You can combine bagging with boosting, and you get something that's similar to what's called stochastic boosting. And if you want to code that up, that would be great fun for all involved. All right, final method of ensembles that we'll talk about today, and it's stacking. Good news, stacking is not hard. Here's the idea. You have some data, and you run lots of different models on it. The models don't have to all be the same family. Maybe this is a neural network, and this is a random forest, and this is a decision tree, and this is logistic regression or linear regression. And they all produce what they predict the output will be. Now, in the past, we've just said, okay, we're done. Let's compare the output with reality. But now, with stacking, we say, you know what? Those outputs could be inputs to yet another machine learning algorithm. And that machine learning algorithm's job would be to figure out how to combine the predictions to come up with the best prediction. So it's like kind of aggregating the juror decisions and coming up with a final verdict. And that is the idea of stacking. Now, here's what I will say about stacking. A lot of people got excited about stacking some years ago. And you would think it would work well. In my experience, though, it doesn't do a lot of harm often, but oftentimes it just doesn't seem to do much good. I'm going to show it to you because it does have supporters. You may see it in the literature, And conceptually, it's kind of related to some of the other work we're going to do on neural networks and maybe some in computational linguistics. So I think it's worth understanding the concept of sort of layers of models. As you're going to see when I do this Titanic stuff, I'm not going to say it would be my first choice to get a good answer to a problem. But let's see what happens. All right, let's load in the Titanic data. We've done that a million times. And here I'm going to come up with three different models, three different classifiers actually. In one, I'm going to cripple it. They're all going to be naive Bayes, but I'm going to cripple them by basically saying, hey, this first model doesn't have access to the cabin class data. I'm going to put everybody in first class. Upgrades for everybody. So now really you can't make a classifier built on first class, on cabin class. By the way, naive Bayes, it's a classifier. We haven't spent much time on it. It uses Bayes' laws to make predictions. It's really fast, and it works surprisingly well, but it's just not competitive with modern machine learning algorithms. But maybe let's see, maybe if we combine it with stacking, we could get somewhere. All right, second classifier, I'm going to not tell it what the age of the person is. Everybody's going to be age 0. And the third classifier, everybody's a man. So no women and children first, because everybody's a man. All right, let's create those classifiers, and it's going to do the first one. Shouldn't take it long. Come on, little naive Bayes. Finish up. It's taking, you know what? I'm going to prove a point. We're going to stop this. I'm going to speed this thing up by setting training progress reporting to none. I think that's going to help it a lot. Copy, paste, and paste. All right, now let's do it. We're done. I was right. That training progress reporting thing makes it slow. All right, let's use the area under the ROC curve that we talked about in connection with confusion matrices as our measure of how good our classifiers are, and we'll run it on the test data, and we'll see how each of those classifiers do. So each of those classifiers depends if we want what we designate as the positive class, but you can see that they're running between 78 and 80, 0.78 and 0.82. So let's see if stacking can improve it. Okay. Here's the idea. What we're going to do is we're going to take the classifiers that we got. We're going to extract the probability that each person survived based on the classifier. Here's the probability they survived based on classifier 1. Here's the probability they survived based on classifier 2. Here's the probability they survived based on classifier 3. We'll apply that to the features, and that'll give us our new training features. Okay, so we have a 916 by 3 matrix, Y3, because we have 3 classifiers, Y916, because that's how many passengers are in the training data. And now we will just put that together with the targets, whether they actually lived or survived, and that's going to give us our training data. That's what it looks like. And now let's build a classifier. And now I'm going to use a fancy method. I did these little methods to build lots of little classifiers. And now for my final assembly, I will use a strong method. I'm going to use gradient boosted trees, which we kind of just talked about in connection with boosting. This is the industrial strength version of gradient boosting. And I am again, I'm very into getting rid of this training progress reporting. Let's do that. And we're done. You can see their industrial strength is a lot better than my hand-wrought one. We've got our classifier function, and let's see how it performs. Our stack classifier performs on data it's never seen before. I'm not going to run through this code because it's exactly the same as we did for the training data. And here we go. Let's see what our area under the ROC curve is. And it actually worked. This is a little bit better than our original classifiers got. But of course, maybe if we just used a, well, you can see that's the area under the ROC curve. I guess I should compare how we do on accuracy. Here's our original accuracy. Here's the stacked accuracy. So didn't make a big improvement there, but we did get better in the area under the ROC curve. The question you should be asking, though, is why don't you just use gradient boosted trees in the first place and not do this stacking business? So that's the hard question. And if these numbers come out better than I got with my stacking, then I'm going to say that maybe stacking, at least in this example, isn't the greatest thing ever invented. And once again, I should have set my training reporting progress thing to none, but we're just going to live with it this time. All right. And let's see. You know, here our stacking actually, the accuracy is about the same. I mean, really close. The area under the curve is a little lower, so didn't do any harm. Maybe it did a little better. And actually, that's pretty typical. What I think is happening is that these modern classifiers and modern predictors are so good that stacking doesn't do that much for you. But what can we conclude? Well, we can conclude that bagging, boosting, and stacking are all ways that, in theory, can produce model ensembles that perform better than any of their constituents, or in some cases better than any single algorithm developed using advanced methods. We'll see these concepts again, basically random forests as an example of bagging plus. You can think of neural networks as kind of being like stacking, and we'll also see shortly symbolic regression, another machine learning algorithm, that's going to use a different method for generating and combining model ensembles. Thanks for a tough video. I will say, as a personal note, this was the most challenging video to make in this course to try and explain some pretty complicated material in a way that I hope is somewhat clear.